students, today we are going to discuss very important isomerism in organic chemistry, that is optical isomerism. It is related to light. This isomerism is also a part of that configurational isomerism, that restriction of free rotation of the molecules. And here only the properties of light is observed, the different property of light is observed. Plain polarized light is passed through the sample of the substance. Then the nature of solution changes. When the light passes through the solution of optical active isomers, then it rotates the light. Which light? Plain polarized light to different directions. Here you see this is the ordinary light source. And when this ordinary light, combination of different wavelength of light, when passed through the nickel prism, this is a very specific prism which allow the light of particular wavelength of light, it will allow, and also allow one plane of light. Then when the mixed light pass through the nickel prism, then one plane of light is produced, a single plane, light produced in single plane. This light is used as plain polarized light, that means in one plane. When this light passes through the sample of organic substance or any optical active substance, if it is optical active, then the sample rotates the light either clockwise or anti-clockwise direction. You can watch the rotation of light, the angle of rotation, that using polarimeter. The instrument is called polarimeter. From polarimeter you can see the movement of light in the particular direction, either clockwise or anti-clockwise direction. So either it will be rotated clockwise or anti-clockwise direction, and the direction of light can be obtained using polarimeter. So two types of optical active isomer is result due to the rotation. If the molecule is rotating in clockwise direction, if it rotating in clockwise direction, through our eye you can also, by watching this rotation, we can identify whether it is rotating clockwise or anti-clockwise. If it is rotating clockwise, that is called dextrorotatory. If rotating anti-clockwise, that is called levorotatory. And dextrorotatory is called plus, levorotatory is minus symbol, and dextro also called D, small d, levo also called small a. And these two isomers, dextrorotatory and levorotatory, just opposite in rotation, but the formula is same, everything is same formula, but only differ in rotation of light. Which light? Plain polarized light, either clockwise will be rotated or anti-clockwise rotated. So these both isomers, combination of dextro and rotator, these two isomers called enantiomer. These two isomers is called enantiomer. Enantiomer means plus and minus. These two isomers are called enantiomers, optically active and mirror image. For example, here one important thing. This is the examples. Here you see COH, HCOH, OHCH, just you see rotation. Here H, OH, OHS, these are two opposite side. And this side also OHH, here OHH, here HOH, just opposite. And these two, if it is plus, it is minus. These two, if it is plus isomer, it will be minus. And these two isomers are what? Optically active and mirror image, because it just looks like opposite. If they are looking like this, if one is mirror image of other, these are called enantiomers. These are called, and these enantiomers are optically active isomers. Very important thing, these are optically active isomers. OAI, short form is OAI, that is optically active isomers. And what these plain polar light, when passed through the optical active isomer, the light will be rotated either clockwise or anti-clockwise. If clockwise, that is dextrorotatory, anti-clockwise, that is levo. And what are the conditions for optical activity? To get optical active isomer, what should be the structure of optical active isomers? The condition is, optical activity condition is, should not have any symmetry element. That means the molecule should not have any symmetry. Symmetry means it should not be plane of symmetry, no axis of symmetry, no center of symmetry. No symmetry is there. That means molecules should not be symmetry. Molecules should be asymmetric. Should be asymmetric. These are symmetric nature. Plane, axis. You have read in mathematics also. Plane of symmetry, axis of symmetry, and center of symmetry. This symmetry if there, then it will not be optical active. We will discuss some examples later. And molecules should have chiral center. What is the meaning of chiral center? Chiral center means for the particular carbon atom, different groups are attached. For example, you see this is called citric acid. This is your that we are discussing. This is lactic acid, tartaric acid. This is your tartaric acid. This is your tartaric acid, and this is citric acid. HCHOH, CH3, COH. This is called citric acid. And this molecule is optical active because it has chiral center. What is chiral center? The molecule, the carbon atoms should attach to different atoms and groups. Here methyl, H, OH and COH all are different. That's why it is chiral center. The molecule is chiral molecule and it is optically active. OAI, optically active isomer. OAI, optically active isomer. So it is optical active isomers. Similarly, you see the example. CH3, if you in place of OH you write another H, you see it is, what happens? These are not optically active because symmetry is there, 2 hydrogen is there. If as it has no chiral center, as it has no chiral symbol is general star, if it has no chiral center, this molecule is achiral and symmetry. And this is chiral and asymmetry. Chiral and asymmetry already discussed. Chiral molecule, asymmetry molecule. Asymmetry means difference should be there. If some similarity is there, then it is optically inactive. That is symmetric elements. That is called symmetric. It is a chiral and is optically inactive isomer. Optically inactive isomer. So these are this very important isomer. So not superimposable to each other. Superimposable means not non-identical. Superimposable means identical. Not superimposable means that is non-identical. They should not be identical. They should not be equal. That's why non-superimposable isomers and having chiral centers and having no plane of symmetry, having no any symmetry. Symmetry should not be there. Then it will be optically active. You see this example already we have discussed. This example, this is a tartaric acid, HOH, OHH, OHH, just differing arrangement. In this case, here this isomer just opposite of this isomer, and it is called plane of symmetry. And it is called your mirror image to each other. As mirror image to each other, and it has and this molecule has no symmetry is there, because if you cannot divide this group in 2 halves, so it is optically active. So if it is plus, the mirror image will be minus. But same molecule if you write in this way, just you see HOH, HOH and OHH, HOH. Here you see the difference. Here this is just opposite. That means mirror image. This isomer is mirror image of second one. So this is first one. This is the first one. This is second one. And this is third one. You can take this is third one. This is fourth one. This is fourth one. This is fourth one. And this third and fourth isomer of this tartaric acid. You see these 2 isomer arrangement just you see. It is one isomer. It is also one isomer. These 2 isomers is mirror image, but optically inactive. It is optically inactive isomer. Both are. Why? Because upper half is just plane of symmetry divided into equally. upper half and lower half is equal, divided in two parts. As it is symmetry is there, that's why optically inactive. OII, optically inactive isomer. OII, and OAI means optically active isomer. It is optically inactive due to plane of symmetry. As it has plane of symmetry, that's why what happens? It is optically inactive isomer. And these two part, upper part is equal to lower part. Both are equal. That's why it is called mesomers. What is mesomers? Optically inactive, but mirror image. Mirror image is there, but optically inactive due to rotation of upper half, lower half in opposite directions. One half opposing the other half. Upper half opposes the lower half. That's why it cannot be rotated in light. That's why it is called optically inactive isomer and called mesomers. It is due to internal compensation. It is called internal compensation due to internal compensation. Internal compensation. These two isomers are optically inactive due to internal compensation. What is internal compensation? Internal compensation means one half opposes other. That's why resulting optically inactive. And here one example just we can see. Here it is different organic compounds having different groups. Here 4 carbon atoms, COH, CE, COH and HCl, OHH. This type of arrangement. Here just reverse, just opposite. So if it is plus, it is minus. If it is plus, it is minus. A plus and minus isomer are called enantiomers. Both are called enantiomer because optically active and mirror image. It is plus means dextro, minus means levo. Both are optically active and mirror image. That's why it is called enantiomers. But you see the different arrangement of this molecule. HCl, HOH, here ClH, OHH. These two isomers you see, if it is plus, it is minus. But if you see this arrangement, which arrangement? One with, let it be, one with third, if you take one with third, these two isomers, what happens? Here, these two, here optically active but not mirror. These two isomers not mirror image. 1 and third is not mirror image. 1 and fourth is not mirror image. And 2 and third is not mirror image. 2 and fourth is not mirror image. That's why, but they are optically active but not mirror image. That's why these are called diastereoisomers. What are diastereoisomers? Optically active but not mirror image. So 1 with 3, 1 with 4, 2 with 3, 2 with 4. These are called what? These pair of isomers are called diastereoisomers because they are optically active but not mirror image. But enantiomers means optically active and mirror image, both relation is there, both satisfy. Optically active should be and mirror image. But mesomers, what are the mesomers? Mesomers means mirror image but optically inactive. Both are mirror image but optically. So these two pairs, the pair of these isomers are called diastereoisomers, which are not mirror image. Mainly they are not mirror image. 1 with 3, 1 with 4, 2 with 3, 2 with 4. These are called diastereoisomers, optically active. Optically may not be optically active, but they are not what? Mirror image. Not mirror image isomers are called diastereoisomers of the same molecule, not different molecules. From the same molecule, two pairs having or pair of isomers which are not mirror image to each other are called diastereoisomers, but they may be optically active or inactive. But optically active plus or minus and plus and minus of the same molecule are called what? Enantiomers. These are called enantiomers. And what are mesomers? Mesomers means that optically inactive and mirror image. Optically inactive and mirror image. If a mirror image there, these are called mesomers and mainly due to internal compensation. But enhance that when you mix plus with minus of same molecule of same isomer of the equivalent amount, then result in optical inactive isomer. That means you complete this one. Next part we will discuss. If you mix plus with minus, plus isomer, if you mix with minus isomer, this mixture of same molecule, mixture of the isomer of plus and minus isomer of same molecule, resulting plus either minus isomer, it is called racemic mixture. Racemic mixture. Optically inactive isomer. Optical inactive. That means racemic mixture is optical inactive. If you mix with the dextro and rotatory of the dextrorotatory and levorotatory of the same molecule, then it will be optically inactive. That is called racemic mixture. And the process is called racemization, preparation of racemic mixture, optically inactive isomer of the same molecule. That is called racemic mixture. If you mix with plus and minus isomer of this tartaric acid, if you mix with that already discussed, that is citric acid plus and minus isomer of citric acid, it will give a racemic mixture, optically inactive. And these enantiomers have same physical property, same chemical property. Enantiomers have same physical, chemical properties but different biological property. Biological property. Biological property are different. For enantiomer, biological property are different. That means plus the biological activity of plus isomer is not same to the minus isomer. That means if plus isomer used in particular medicine, minus will not be used for the same medicine. That's why biological property of plus and minus are different, but physical property, chemical property almost same for the enantiomers. Then I will give some examples which are optically active or inactive. If structure is like this, if you write this, it is optically inactive. Optically inactive isomer because it is plane of symmetry is there. Then this molecule okay, this is suppose H. This molecule is optically active isomer because it is having chiral center. It is having chiral center because Y, X, methyl, H all are different. That's why it is optically active. This is also optically active. This is also optically active isomer. And some other examples like this. It is optically inactive because it's planar, plane of symmetry, double bond is plane of symmetry, it is optically inactive isomer. But allenes Allene's group having this type of isomer, suppose H, this is your CH3, this is your CH3, suppose this is H. This type of molecule is optically active. Optically active isomer, because what happens, if you see this double bond and this double bond, this molecule will not remain in the plane, they will remain like this. Just look at me. If it is one plane, if the one C double bond C is in this plane, then C double bond C will be not like this, it will be like this, vertically cut, it will cut to another plane. So in this type of arrangement is not planar molecule, it is non-planar. If the molecule is non-planar, then it will be optically active. So it is optical. This is allene. Examples are allenes. Allenes groups are optically inactive, but the different groups will be attached. If both will be HH, it will be optically active. If it is HH, it will not be optically active. So having different groups attached and double bond adjacent two double bonds, it will be optically active. Biphenyl groups also optically active. But if you say only this molecule, it is optically inactive. It is optically inactive. But two biphenyls, two groups are joined like this. Two groups, it will be optically active. Because what? Same, if one benzene in one plane, other will be just vertically. These two will be in vertical position. That's why they will not be in plane, same plane. That's why it is optically active. But this type of molecules or having any group, bulky group is there. Suppose it is R. Suppose it is R. Here are, then they will cause repulsion, so that they want to remain in different plane. So if this benzene having R in this plane, then other benzene 2R will be in another plane. That's why it will not be planar molecule. That's why it is also optically active. So these are some important examples of optically active isomers. Optically inactive isomers, what are diastereoisomers, what are mesomers, what are the properties of enantiomers. Enantiomers having same physical and chemical properties but different biological properties. And diastereoisomers, these diastereoisomers, they have different melting and boiling points. Melting and boiling points are different and their chemical property also different. So these are some important concepts regarding optical isomers. This mixture of mixture of this plus and isomer of same molecule is called what? Racemic mixture, optically inactive. And which molecule will be optically active, which molecule optically inactive? Let us discuss from plane of symmetry, center of symmetry and axis of symmetry. Okay, you complete it. Let us discuss which molecule has what type of symmetry elements. For example, water. Here water is, if you rotate the water through oxygen atom in this axis, then by two-fold axis, 180 again 180, completely rotate, then same molecule will be repeated. Once and twice if you rotate, the same molecule will be rotated. For example, if you can do like this, suppose this is water molecule, if you rotate first, it was like this, first, then second, like this. If you rotate, same molecule will be repeated, same position it comes. After rotation, after two-fold rotation, same position they will attain. That's why it is symmetry. It is called axis of symmetry. This is axis of symmetry. Axis of symmetry. This is three-fold axis of symmetry. This is three-fold axis of symmetry. It is two-fold axis of symmetry. This is plane of symmetry. If you fix here, then this side is equal to this side. Plane of symmetry. This is plane. This is your center of symmetry. You see, methyl is upward and here methyl is downward. If you toss this group to this group through center of this molecule, then H also coming, same atom is repeating, methyl also coming, methyl. So it is called that center of symmetry. Through this center, if you join atoms and groups above to below, if they are coming same group, same atoms are coming again, that is called center of symmetry. This is called center of symmetry. Center of symmetry. This is also fourfold axis of symmetry, and this is plane of symmetry. This is plane of symmetry. So these are the different types of symmetry elements. If molecule have symmetry elements, then it will not optically active. For the optical activity, molecule should be asymmetric in nature. Asymmetric means should not have any symmetry elements. Then it will be optically active. Okay, you practice. In the next class, we will discuss that how many number of diastereoisomers, how many number of enantiomers will be possible, how many types of mesomers will be possible from the particular that isomers having more than one carbon atom. Okay, thank you.